In this tutorial, I'll show you how to solve the problems on homework number 5. So the first section is on solving multi-step equations. So in question number 1, you'll notice that on the left and the right side there are x's. So the goal is to get those x's together so that you can isolate the variable. So the first thing I'm going to do is take a look over here on the right side of the equation where the parentheses are. You can't use any inverse operations until after you have cleared these parentheses. So I'm going to distribute my coefficient of 2 to each term inside the parentheses. The left side remains the same, and the right side will be turned into a 4x, 2 times 2x is 4x, and 2 times positive 3 is positive 6. Now what I'm going to do is get my x's together on the same side of the equation by using an inverse operation. So I'm going to subtract this 4x over here, which is an additive inverse, which would give me 0. That means only 6 is left on the right-hand side. Now if I'm going to subtract 4x on the right side, I need to subtract 4x on the left side. And this is an interesting problem because on both sides, the variable term cancels out. And when I bring down the remaining constants, they are exactly the same. 6 is equal to 6, and since that is a true statement, there are an infinite amount of numbers or infinite solutions to this problem. An infinite amount of numbers can be plugged in for that variable x and still make this equation true. Let's take a look at question number 2. You'll notice the left side has 2 terms and the right side only has 1. So that means I'm not going to do any math with the 6x, because if I use an inverse here, then this side would be empty, and we don't want that. So I'm going to subtract 7x from both sides of my equation because those are the like terms. So here I get an additive inverse, and when I rewrite, I get 4x equals negative 1x. So from here, in order to isolate x, I need to remove any coefficients or any negative signs. So the inverse of multiplying is dividing both sides here by negative 1. And that gives us a solution of negative 4. So there's only one solution to this problem, but there were an infinite amount of solutions to the previous problem. Okay, let's take a look at question number 3. In this problem, again, the left side has more terms, so I'm going to use one of these terms. Now, I'm allowed to do this. It is equal and fair, but it doesn't make my problem any shorter because these two are not like terms. So even though I'm allowed to do this, it really isn't very productive. So let's rethink which term we should actually be using an inverse operation on. So since I have a constant term and a variable term, the one I'm going to choose depends on what's on the other side. So if the other side has a variable term of x, then that means I'm going to use an inverse of the x term. So I'm going to subtract 2x from both sides here. By doing that, I cancel the x's on the left, and I get new math here on the right. I'm going to divide by my coefficient, not the answer, but by the coefficient of 6. And be careful with your math here. It's 3 divided by 6. Not 6 divided by 3. So the answer is 1/2 or 0.5. All right, let's take a look at the next two problems. So question number 4 does have a coefficient, but the coefficient is a fraction, 1/2. So I'm going to multiply 1/2 times both of these terms inside, but not this one because it's not inside the parentheses. So 1/2 times 4 means 1 times 4, which is 4, and then that answer divided by 2. Half of 4 is 2, and the x comes along with that term. And half of 24 is 12. Now I can remove my constant and combine these terms here. Now that they're both together, this is called combining, but this is an inverse operation here. So 2x is equal to 4. Divide both sides by 2, the coefficient, and get my one solution. All right, let's take a look at question number 5. We haven't seen this on this worksheet yet. You'll notice that the right side of the equation has actually 3 terms, x, plus 2, and minus 7x. So when you have these 3 terms, the side can be simplified, right? You can do some combining. So the terms in which you combine have to be alike. So I'm going to use this little loop here to show that these 2 terms, 1x and minus 7x, can actually be combined. So I'm not going to use an inverse. I'm not going to do the opposite. So don't do this. I see this a lot and it's very, very wrong. Do not do this. That is not fair. You see this? This is the side splitter. And if you write that, you've broken a rule and you've done 2 things on one side and nothing over here on the other. So that is not a correct inverse property here. That is not a property of equality. So we're going to draw this loop to show we're going to combine them. And when you combine, you do the math that it says to do. If it says minus, you minus. This says x minus 7x. So I'm going to leave this side alone, and I'm going to combine. 1x minus 7x makes negative 6x. And I bring the plus 2 down here. The next step is to get my x's together on the same side. I'm going to choose to do the inverse of this variable term so that my variable stays positive. So 10x plus 8 is equal to 2. And now I'm going to subtract 8 from both sides. And I'm going to get 10x equals negative 6. I'm going to divide both sides by 10. And I'm going to get one solution of 0.6. All right, last one. This one contains a decimal. So 0.4 is my coefficient, and I am going to multiply that by x and by 2. So 0.4 times x is 0.4x, and 0.4 times 2 is 0.8. Marker's not work. There we go. And I bring down the answer on the other side here. So I'm going to use my inverse operation here. Subtract 0.8 on both sides. I get 0.4x equals negative 18 minus 0.8. So I'm going to get negative 18.8. I'm going to divide that by 0.4. So I'm going to divide that by my coefficient. And I actually get negative 47. All right. Let's take a look at the next section. The next section is a graphing section of coordinate points. Whoops. Let's back up. Here we go. So the directions say graph the coordinates on the grid below and label it with the correct letter. So when you label it, that means that you write a letter, right? Label it. You write a letter next to the point. So you have to be writing the actual dot, right? So 0 on the x-axis and negative 7 on the y-axis. So 0, negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7. That actually is off the grid. All right. Letter B. 4 on the x-axis. That means 4 to the right. And 1 on the y-axis. So 1, 2, 3, 4. And 1 on the y-axis. So we'll label that B. Letter C. Negative 2 on the x. That means we go to the left. Negative 2 on the x-axis. And 1, 2, 3, 4, 5 on the y-axis. So we'll label that with a C. Letter D. 3 on the x-axis means 3 to the right. And 0 on the y-axis means nowhere up or down. So I'm actually going to stay right on that axis. Letter D. Letter E is negative 2, 0. So that one is also on the axis, but over here. And then the last one, letter F, is 2.5. So I'm going to go halfway. And then negative 1, negative 2, negative 3, negative 4, and then halfway. So it's going to be right in the middle of a box there. And that is letter F. So all the points were graphed and labeled. All right, let's turn the paper over to the back side and let's take a look at the next equations to solve. So the directions here say to tell whether the equation has one solution, no solution, or infinite solutions. Well, infinite solutions means that the left side and the right side are an identity, which means that they exactly match. And that's kind of tough to see on some of these, but I think for number 13 you can tell already. 3x plus 1 is equal to 3x plus 1. So when they match perfectly or exactly, we call that infinite solutions. And we can prove it by subtracting 3x from both sides and making a true statement. Yes, 1 is equal to 1. Now you see for number 14, these are not equal on both sides, but that doesn't necessarily mean there's no solution. In order for there to be no solution, the variable would have to disappear and the sentence would have to be false. But when I do my inverse operations here, my variable never goes away. It's always there. See that? 4 x's. And even after I divide, I still have the letter x. So this one is one solution. There's one solution. 3 is the only number that will work for x to make this sentence true. For question number 15, these don't match exactly. See, this has a plus 6 and this has a minus 6. So I'm going to use an inverse operation here just to find out for sure if it is infinite solutions, no solutions, or one solution. So you notice my variable m, it's gone. So that means I have one of these special cases. And since this statement is not true, it does not have a solution. No solution. Not true, but it actually should say no solution because it is not true. No solution because it is not true. But the only reason I can say that it's not true, just like this here, they don't match either, but this one has no variable anymore. That's why it's no solution. All right, over here, let's do our distributing first. 2x minus 8. And this one is no distributing over to here, so 6x plus 8. So I'm going to minus 2x from both sides. I'm going to get negative 8 equals 4x plus 8. I'm going to subtract 8. I'm going to get negative 16 equals 4x. And then I'm going to rewrite it over here. If I divide both sides by 4, I get one number on the left and one letter on the right. So this is one solution. Now let's take a look at this last one here. So if I minus 3x, and I take a look here, does the variable actually go away? This isn't not an inverse, but this one is. You see the difference? A plus and a minus, but this is a minus and a minus. So I actually get this. And then when I subtract 5, remember that minus sign belongs to 6. So I'm going to subtract 5 here, get negative 6x equals 8. I'm going to divide by negative 6 here. Right? I'm going to rewrite this up here. And these are inverses. And 8 divided by 6, 6 does not go into 8 evenly, but I could say that this is the same as negative 4/3. I'm going to leave it in fraction form because the answer is 1.333333333 forever. All right, let's take a look at the last box. How to graph a line graph, which means I should have a straight line like this. So let's put our labels down. Number of days, that's the x-axis. Amount earned, that's the y-axis. So I'm going to label that here. Number of days. And over here, we're going to write amount earned. All right, now next thing is I need to make a scale here. Remember, your scale needs to be consistent. You can't put a 1 here and then put a 2 here and then put a 3. You can't do that. See that? This means one box is 1. So that means one box has to be 1. So you need to be consistent with your scale. If you want to go by ones, that's fine. If you want to skip count and go by double boxes, let's see if that would fit. 1, 2, 3, 4. Ooh, it just fits. So you want to check that your scale can fit all of your data. Now let's see over here, 30, 60, 120, 150. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. That won't be enough to go by 10s. I could go by 20s, but then I'd have to do an in-between graph here and an in-between graph here because 20 doesn't go into these numbers. So if I look at my data, it looks like they're all multiples of 3. 3, 6, 12, 15. See that? So I'm going to go by 30s. 30, 60, 90, 120, 150, 180, and it looks like that's as high as I need to go. So let's start graphing. At day 1, the amount earned was $30. On day 2, the amount was $60. On day 3, the amount was $120. And on day... Oh, sorry, I just graphed that wrong. I wasn't paying attention. Day 4 is $120. Day 4 is $120. And day 5 is $150. And if I connect it now, it should make a straight line. Now that makes sense. Remember before I tried to graph 3 at 120? That would have made a crooked line. See that? So then maybe I would have noticed that I had to go back and redo it. Okay? I can extend this line down if I'd like to the origin, but I'm not going to extend it below the origin because that doesn't make sense. You can't have less than 0 days and you can't have less than $0. I bet you could earn more, so I'm going to put an arrow here like that. And that is how you complete homework number 5.